Hi everybody and welcome to Chem Talk, where today we will be going over electromagnetic energy and go over some examples on how to apply it to chemistry. So let's talk about it. Let's begin with some general definitions. Electromagnetic energy or radiation is electric and magnetic fields that move in waves as opposed to individual particles. Waves can be defined as the oscillating motion in which the electromagnetic energy moves. Waves have both frequency and wavelength. I'll draw a small wave over here to get a visual. Wavelength is the distance between two peaks of a wave, often measured in nanometers. And 1 nanometer is equal to 10 to the negative 9th meters. One wave cycle is the length of a wavelength, and frequency is the number of cycles over a certain amount of time. This is often measured in the unit Hertz, often abbreviated Hz. First, it is important to note that wavelength is denoted by this symbol and frequency by this symbol. Wavelength and frequency are inversely proportional, meaning the shorter the wavelength, the higher the frequency, and the longer the wavelength, the lower the frequency. Wavelength times frequency equals the speed of the wave, and since all forms of electromagnetic energy travel at the speed of light, we can also say wavelength times frequency equals the speed of light, which is about 3.0 times 10 to the 8th meters per second. Additionally, there is something called the amplitude of a wave, which is the height of a peak. This can be denoted as a capital A. Amplitude is proportional to the intensity of the wave. In terms of light, a higher intensity corresponds to a brighter color. The energy, measured in joules seconds, can be found with the equation E equals h, or Planck's constant, times frequency. Planck's constant is a value that is called a constant because it is always the same number. It is 6.63 times 10 to the negative 34, no matter what. Energy and frequency are directly proportional. Now let's try a quick practice here. Calculate the energy and wavelength of a photon of light with a frequency of 5.63 times 10 to the 14th Hertz. First, we'll use the equation energy equals Planck's constant times frequency. Substituting in the values we know, we can solve for energy and get 3.74 times 10 to the negative 19th joules. Then to find the wavelength, we can use the equation c, or the speed of light, equals wavelength times frequency. Again, substituting values, we can solve for wavelength and end up with 5.34 times 10 to the negative 7 meters. Note how this is meters. In order to convert to nanometers, we must multiply by 10 to the 9th and get 534 nanometers. There is something known as the electromagnetic radiation spectrum. We begin with radio waves. These have the largest wavelength and the lowest frequency. Next is microwaves. And if you're now thinking of the kitchen appliance, you wouldn't be wrong, as that is the very type of radiation that microwaves emit. Next is infrared radiation. It's interesting to note how infrared comes just before the visible light spectrum, which starts at red. This is because the prefix infra actually means below, and infrared radiation is just below red. The visible light spectrum comprises all the energies of light that are visible to the human eye, so red through violet. Beyond violet, we have ultraviolet. You may recognize this as a type of radiation emitted by the sun. Next comes X-rays, and then finally gamma rays. Something to note is that as the frequency increases, how harmful each type of radiation is also increases. Radio waves certainly don't do much damage, but gamma rays are deadly. Now let's talk about something called the photoelectric effect. It was observed that when light was shown at a metal beyond a specific frequency threshold, electrons from the metal were ejected. This became known as the photoelectric effect. Taking a look at the Bohr model of, let's say, sodium, we can see that electrons exist in discrete energy levels around the nucleus. When hit with the light, electrons gain energy. The key thing here is that electrons cannot exist between energy levels, so the energy the electrons gain must be above the minimum threshold the electrons need to gain to reach the next energy level. If it is not, nothing happens. Once the electrons reach the next energy level, they are in what is called the excited state. However, electrons are unstable when in the excited state, so they release the energy in order to return back to their original state, or ground state. They release this energy in the form of electromagnetic radiation. This idea requires one to view light as a stream of individual particles, rather than a single wave. This is why light has been given the name wave-particle duality, the idea that light has both wave and particle-like qualities. Sometimes this electromagnetic radiation that electrons emit can fall in the visible light spectrum. This explains why some chemicals produce different colors when burnt, as when you add the flame you are adding energy to the electrons. For example, potassium burns a beautiful lilac color. What researchers have observed is that each element has a unique spectrum of colors it can emit. This relates to the idea that every element has a unique set of energy levels that each require unique amounts of energy to reach. Since the energy of the electromagnetic radiation released by excited electrons is the same as the energy they require to become excited, these elements also release unique energies of electromagnetic radiation and thus unique colors. Let's look at hydrogen's atomic spectra, for example. We see that the difference in energies between each level accounts for these specific colors. Also note how it is not one continuous range, but rather discrete energies and discrete colors. This again relates to the concept of discrete energy levels and how electrons cannot exist in between them. As red is produced by lower energy electromagnetic radiation, and the energies of energy levels increase as you move away from the nucleus, it can be concluded that as you move across the spectrum, the colors correspond to the amount of energy the electron released. Since these emission spectrums are unique to elements, they can be used to identify elements. Let's do one more practice. Here's some known information. Wavelengths correspond to specific colors. For red, that's between 740 and 625 nanometers. For orange, that's 625 to 590. For yellow, that's 590 to 565. Green is 565 to 520. Light blue is 520 to 500. Dark blue is 500 to 435. And finally, violet is 435 to 380 nanometers. The question is, what color would a photon of light with an energy of 3.21 times 10 to the 19 joules produce? First, we use the energy equation. Energy is equal to Planck's constant times frequency to calculate the frequency. Next, we can use the equation the speed of light is equal to wavelength times frequency to calculate the wavelength. We get 6.2 times 10 to the negative 7 meters again. And to convert to nanometers, we multiply by 10 to the 9th and get 620 nanometers. Looking at our spectrum here, we can see that falls in the red range of wavelengths. So we'd produce a red, probably red-orange color, since this is nearly on the barrier between red and orange. So in conclusion, electromagnetic radiation is electric and magnetic fields that move in waves, as opposed to individual particles. Photoelectric effect deals with the concept that there are minimum thresholds of energy that must be met for an electron to be ejected or moved into an excited state. The atomic lines, or spectra, is the idea that every atom produces a unique spectrum of colors due to the unique amounts of energy required to travel between energy levels. Finally, some important formulas to remember is that the speed of light, or c, is equal to wavelength times frequency. Energy is equal to Planck's constant times frequency. And you will get wavelength in meters, and to convert 1 meter is 1 times 10 to the ninth nanometers. So that's all for today on electromagnetic energy. Thank you for tuning into ChemTalk. Make sure to visit our website www.chemistrytalk.org for hundreds of general, organic, and biochemistry articles.